Recording? Yes. And share my screen. Okay, welcome to data mining for today. Two quick announcements before we get started. I was mentioning before starting the recording here that I am going to be gone over fall break for a conference in Korea. And because of that, I'm actually leaving Wednesday after our class. And so there won't be any like office hours Friday. I won't be available. And I guess Tuesday is part of fall break anyways, but I'll be getting back on Tuesday. So that's not, there wouldn't be office hours then anyways. And if there are any questions that people have or anything, I'll probably be unavailable until like next Tuesday. So emails, expect slow email or GitHub issue replies. In terms of our approximate timeline or like how things are going in this class, again, you have this coming Wednesday, your next quiz and the material for that quiz. There we go. This one here. All the stuff in boxes are the definitions that you'll have to have memorized, and you'll barf it out onto the quiz paper, and hopefully you'll get it all right and get full credit on the quiz. Again, the way the grading on the quizzes works is that if you don't get full credit on the quiz, then you'll have to keep retaking the quiz until you do get full credit, until you do get all the definitions. And each time you have to do a retake, then it results in a -1% penalty on your final grade in the class. Any questions on the quiz? Okay. Other things, there we go, coming up. So today we'll finish up pretty much the statistical stuff that I want us to do before the next midterm. And then we'll have 2 more class periods this coming Wednesday and the Wednesday of the fall break week to talk about the computational things. And that'll be it for the midterm 2. And so the actual midterm itself will happen approximately 3 weeks from then, last week of October. In the meantime, between all that, there will be another project. The project's actually already posted, and we'll get to talking about that today. Any questions on anything administrative, timeline-ish stuff in the class? Yes.
Do you expect to be like that Thursday or Sunday?
Yeah, if so I'm super flexible. I have no strong opinions. If people liked that sort of time frame of like Thursday to Sunday, then we'll keep doing something like that. It will be a take-home sort of fully open note thing like the last one. If for whatever reason that sort of time frame didn't work for you, then let me know and I'll think about something different. And again, we'll have like these 3 midterms that are take home like this, and then your final in the class, which is the most heavily weighted thing in the class, will be in person. Good question. Any other questions? Anything administrative, timeline? Okay. Ooh, I forgot to bring up my little pad. We're going to start today talking about a little bit of review stuff for the quiz. This right here that I have is the opened up is this training versus testing notes number 2. This thing that has just a whole bunch of problems on it. And this the problems in particular are designed to test your understanding of the definitions. All the problems follow somehow immediately from the definitions. And so I want us to look in problem number 2. We'll take a look at this part 12 of problem number 2 to start with. And there we go. So on all these problems, again, they're all going to follow somehow immediately from the definitions. And so the first thing that you should do after reading them is basically remind yourself what are the definitions of everything. So this problem number 12 right here asks if a hypothesis class H shatters some data set of size n, then this mh of n thing equals to the n. One of the habits that I like to be in is whenever you see some sort of like notational equation thing, one of the things that, or one of the options that you have to read this in your head is to read it syntactically, like saying, like I just did, saying mh of n. But that's not really a good like memory jogging thing of like, what is this meaning? So actually, when I'm reading this, I like to read it semantically and not read it as mh of n, but read it as the growth function. And so in my head, as I'm reading these statements, I'll say, if the hypothesis class H shatters some data set of size n, then the growth function is 2 to the n. And that just helps remind me, I think, a little bit more about like exactly what these definitions are and why we care about them. Because it's just easier to remember things like growth function. But whatever works for you is fine. So the growth function and the shatters are the two definitions that are important for this particular problem. Let's head back over to our definitions over here and let's find growth function, this thing right here. So the growth function, again, is somehow the maximum of this like H thing over here. And this H thing over here is the dichotomies of our hypothesis class. And the dichotomies, again, are all the possible labelings of every data point in the hypothesis class. And one of the things that's not on this this fact sheet right here, or this quiz sheet right here, but it was on the actual notes, is that the maximum possible number of dichotomies that you have is 2 to the n. That's just the biggest that the size of the dichotomies can be, and so it's the biggest that the growth function can be. And so looking back over here, 2 to the n, this is like the biggest somehow possible growth function that we have. And then this idea of shattering, back over here, is definition 7. We say that a hypothesis class H shatters a data set, or can shatter a data set, if any of the following is true. And down here, this number 3 is the one that's going to be important for us right now, is that it's the number of dichotomies is equal to 2 to the n. It's the biggest number of possible dichotomies. And so this growth function right here is the maximum number of these dichotomies. This shattering means that we're at the maximum at this 2 to the n level. And so coming back over here. So if the hypothesis class H shatters some data set of size n, then by our definition of shatters, we know that for that data set, H of the x1 up to x sub n is equal to 2 to the n by the definition number 3 of shattering. And the growth function was the maximum of the hypothesis of the dichotomies. And the maximum value was 2 to the n. So this is going to be a true statement. So it's a true statement. And again, the argument is that this is the definition of shattering. Shattering implies that the growth function mh of n is the max over all data sets of h x1 up to xn, which is always less than or equal to 2 to the n. And so since we've found something that's equal to 2 to the n, and we're looking at the maximum, and the biggest one can possibly be to 2 to the n, then this m right here must be equal to the 2 to the n. Shattering, this is all basically by definition. Shattering implies that mh n will be equal to 2 to the n. In terms of like the actual, so again, the quiz on Wednesday, there's not going to be any problems like this. The quiz is just on the definitions, but on the midterm exam, there will be problems, something like this. And exactly what you write down here, as long as it's somehow something reasonable that supports the claim of either true or false, will be given full credit. Any questions on this particular problem?
Can you go back to the definition of the shattering? Can you just elaborate on the second possible criteria?
So the question is that we use number 3 on the problem, but what's the deal with number 2 right here? Okay. So number 2, this is a sort of strictly notational thing when we have this set of -1 or +1 to the n, when it's talking about, so I'll say as an example, -1 or +1 to the first, that's just equal to the set of -1 or the set of +1. And then the set of -1, +1 squared, that's equal to, and I'm not going to have room here to write it all, but I'll do what I can. Whatever you have up here in your exponent is the size of the tuple. I put parentheses around here when it's not strictly necessary, and actually one of these should be a negative, one should be a positive, because you should think of these as like tuples of size 1. Here the tuples are of size 2, so it'll be like all possible tuples of size 2, -1, +1, +1, -1, +1, +1, like that, all the possible tuples of size 2. And so the reason why on 3 right here, while we have this, the absolute value or the size of this particular set equals 2 to the n, is because the number of tuples that we have is n, or the size of the tuples is n, and we do all possible combinations of +1 and -1. And so there are 2 to the n possible combinations of these tuples, filling them in with +1 and -1. Good question. Any other questions on the definitions or this problem? Okay. Again, for the quiz itself, it's like you just have to know the stuff in the boxes and you'll be good. Maybe some of the more subtle ones, I guess, is this, the definition of shattering. I'm asking you to remember all 3 of these possible definitions and reproduce all 3 of them. For the VC generalization bound down here in the actual notes, there was several different versions of this formula down here. If you prefer to remember one of the previous ones, one of the other versions for whatever reason, you're welcome to. One of the strictly more powerful ones. But here, the big O notation is the one that's the most useful, I think. So that's the one that I put here. But any of the versions would be fine. Let's come back over here. Let's do another problem. So the reason we're doing these problems right now again is that I think doing these problems will help you understand the motivation for all of the definitions, and understanding the motivation for the definitions will help you actually remember the definitions. So problem number 13 right here, there exists some hypothesis class H with growth function mh of n equals theta of 2 to the square root of n. And the growth function, again, is the biggest possible number of dichotomies. And one of the theorems, actually, that we stated in class, but is not on this definition sheet. The only theorem on this definition sheet on the quiz is the VC generalization bound right here. But one of the other theorems that, here we go, that we talked about is this one right here. This is the notes from the first notes from chapter 2, the one previous to the problem set. And this says that either the growth function is exponential of the form 2 to the k, or it is polynomial of this form, and it can't be anything in between. And so for these problems on the midterm, sometimes just knowing the definitions won't quite be enough. You'll also have to know those other theorems, refer to them. And you don't have to have them memorized, but you at least need to know that you should be able to look back at those theorems, roughly what they say, when they might apply. And here, when you have theta of 2 to the square root of n, well, this is neither polynomial nor exponential. And so this must be false, because the theorem that we just looked at, and that theorem, sometimes called Sauer's lemma, it's called Sauer's lemma in the book. Sauer, oh, I don't even know how to spell his name. That's not how you spell his name, but that's what I'll write. I think it's theorem, we'll do theorem 1 on chapter 2 notes. Says MH must be either theta 2 k or O of n to the k. And this is neither of those things, so it must be false. Any questions about problem 13? Okay, let's go ahead and do problem 14 since it's on the page. We'll finish out the page. It says let H be an arbitrary hypothesis class, then MH of n, the growth function, is equal to O of 2 to the n. And here, this one is, so the first one was really testing your knowledge of the definitions. This one, number 13, testing also your ability to refer back to previous theorems and know that those theorems exist. Problem 14 here is really only testing your understanding of big O notation. That our fact was that MH of n is always less than or equal to 2 to the n. And this big O up here is an upper bound again. We've seen some growth functions that grow polynomially, like this. But since this is an upper bound, the polynomial growth functions will still be upper bounded by an exponential. And so this is true. Just by definition of big O notation in this fact. Any questions about that? Super easy problems? Couple head shakes. Yeah, once you've mastered the definitions, they will be, I think, super easy problems. Understandable if you haven't mastered the definitions yet, but that's the goal, master the definitions, so these become super easy problems. All these definitions, again, they're building up to this VC dimension generalization bound theorem right here. This theorem is so important that it's often called the fundamental theorem of statistical learning. And we're going to be applying this theorem to understand how we should adjust our learning problem in the face of different situations by adjusting our VC dimension or collecting more data or these types of things. So now coming over to last time, we started with these chapter 3.4 notes that, again, we skipped chapter 3.1 to 3.3, the very beginning part of chapter 3, because that mostly focuses on computation. And I wanted to do all the statistical stuff together. And then starting next class period, we'll go back to chapter 3.1, talking about the computational aspects of things. And the key idea of this section is that we had this phi function or feature map, feature transformation that somehow let us manipulate the VC dimension of our problem and therefore manipulate the generalization error of our problem. The most important of those phi functions is right here, this polynomial feature map, where we can expand our VC dimension to what we want it to be. And the polynomial feature map, again, the sort of intuition behind it is it's like the Taylor theorem that allows you to approximate any one-dimensional function by polynomials. Well, you can also approximate any arbitrarily high-dimensional function by polynomials. And so as we increase the dimension of our polynomial feature map, our En is going to go down arbitrarily down to 0. And so we have this universal approximation property. Last time I showed you this video right here that somehow mapped this like two-dimensional space, this circle down here. This is not a linearly separable data set down here, but when we applied the polynomial kernel in degree 2, we get this third dimension up here, and we become linearly separable in this higher dimension. And that's the key sort of like intuition why we care about these feature maps, is if we transform our data somehow, then we can make the problem easier. Either easier in the sense of better training error or easier in the sense of better generalization error. Whoops. And then after talking about the polynomial feature map, we started talking about, here we go, this PCA feature map. We're going to continue this discussion here in a second. But before we do that, we're going to jump over to your next programming assignment, which will be about this polynomial feature map. In the class GitHub repository under this week 4, I've added a folder project right here. And inside of this project folder is this IPython notebook file and a README. So the README just has some overview on how to run this file and the due date. So the due date will be the end of fall break. Again, if you do the collaboration, then you can get the 2-day extension to Thursday. And at this point, we've actually covered all the material that you need for this. So you can get started on it right away, finish before fall break if you want. Or if you don't want to, you can do it after fall break as long as you are collaborating with other people. In order to run this Jupyter Notebook file, this is the command that you would type in the terminal. And I'm going to go ahead and do that on my laptop real quick so that you can see what it might look like. Here we go. So I'm in the project folder. Here's the thing. Copy and paste this command over there. And when you do that, it's going to open up a bunch of stuff, give you a URL down here to go to in Firefox if it doesn't automatically take your browser over there. And then you click on the half spaces polynomial like that, and it will open this up. I'm going to go ahead and open up the solution, and we'll take a look at the actual solution part here. I'll also, quick aside, so some of the things I've scaled down a little bit the runtimes of things so that you can do this all on your own laptop if you don't want to do it on the Lambda server. On a laptop, it might take about 15 minutes for some of the computations to run. On the Lambda server, it's everything should happen less than a minute. But it might, if you haven't used the Lambda server, it might be a little bit weird getting it set up because you'll have to do something called port forwarding. But if you don't want to do that, you can just run it on your own laptop and that'll be fine. Okay, so here's what the solution to this looks like. Let's zoom in. These, let's first of all, so we've been talking about perceptrons a lot. In all of these notes, instead of talking about perceptron hypothesis class, I'm being slightly more general, talking about the hypothesis class of half spaces. But this is entirely equivalent to the perceptron hypothesis class, just a different, slightly more generic name for it. And the idea of this set of this assignment is for you to just sort of play around with different hyperparameters on synthetic data, making your own data sets and seeing how these like F functions, G functions, hypothesis classes, the dimensionality, VC dimension, all these weird abstract things relate to each other. After this assignment, we'll be getting into real data assignments, but the disadvantage of real data is it's much harder to like manipulate all of those functions and get a good sense of them. So this first one is with synthetic data so that you can get a better sense of all those different definitions. There's a lot of pre-existing code in this IPython notebook. In order to run it all, you have to go through and press run on everything. It'll plot things like graphs of the VC dimension for you under different situations. We talked about how the VC dimension of the polynomial kernel is sometimes grows polynomially and sometimes grows exponentially. And reading through the code, you'll be able to see exactly why these things correspond to those situations. There's 11 questions throughout this notebook that I'm asking you to answer. All the answers, you just double click on the question like I just did and type your answer down below down here. I'm not looking for super extensive answers for anything, that they can all be answered in just like 1 to 2 sentences is fine. Keep going. There'll be some things that ask you to plot different data sets and with noise and higher dimensions and various situations. Eventually, you'll be making plots that look something like this. On these 3 plots right here, for example, we have the number of training samples on the x-axis, and then the 3 plots are the training error, the testing error, and the generalization error. And so you'll be able to see exactly how the VC dimension theorems that we've been talking about predict all of these graphs. And you get some occasional slight hiccups, but these things do follow the formulas that we've been talking about pretty closely. Yeah, as you go through it, there's, I don't know, you're very likely to run into questions. So I recommend not putting it off until the last minute so that you have a chance to ask those questions. But at least from like a programming perspective, this is all pretty straightforward. It's just a matter of thinking about how the theorems apply to all the graphs, and the programming should be straightforward. The hard part will be, thinking about the math of all the things we've seen and how it relates to the graphs. Any questions about what to do, how to get started on something like this? Yeah. Wherever you run the command is the computer that is going to be running all the code. So if you run it on your laptop, then some of these function calls might take up to about 15 minutes. If you first log into the Lambda server and run it, then the functions will go faster. But you'll have to figure out how to get Firefox connected to the Lambda server, which might be hard if you haven't done that before. I'd be happy to, anybody who hasn't done that before, to like show you in office hours or after class sometime how to get that set up. Good question. Any other questions? Okay, then on to the fun stuff for today, all the math. So yes, we've reviewed up to the polynomial kernel. The polynomial kernel is again super important because it lets us increase the VC dimension and so decrease our training error. The main idea of the PCA feature map is that it's a dimensionality reduction technique. So we reduce the VC dimension, reducing our generalization error. And I said I'm not going to talk in too much detail about exactly the intuition behind why we might want to use eigenvectors of this A transform right here. But I do want to show you a couple of pictures. And these pictures have links in the other embedded in the LaTeX and the PDF files. But here's an example image classification data set. And so here's a bunch of images of famous American politicians or British politicians. And if you were to calculate the eigenvectors of these images, this is what those eigenvectors look like if you plot them. So they're sometimes called eigenfaces. And so you can maybe imagine that these somehow capture the shapes of the faces instead of having a 500 dimensional vector, one for each pixel. If your vector is how well the dot product with each of these shapes match, then you're going to capture a lot of the information about the images in fewer dimensions. So this is a good thing to take a look at if you want that eigenvector intuition. But ultimately, in terms of generalization error, the things that we care about, the how that A matrix is determined doesn't matter at all. That our VC dimension is going to be theta k, where k is the number of eigenvectors we're picking, is the shape of this A matrix right here. K equals d prime, the output of our dimensions. So this next problem number 3 is another one of these linear feature maps. Again, it's a linear feature map because this function right here is a linear transformation of the original data. And we know it's linear because we have a matrix right here that we're multiplying by our input vectors. This feature map is the random feature map. And so this A matrix right here, whereas previously the A matrix was somehow defined based on the data, doing these eigenvector things that we didn't really talk about, and maybe you don't have a lot of intuition for, but people talk about eigenvectors a lot, so it seems like somehow eigenvectors might make sense. But this A right here is defined to just be totally random somehow. And in particular, people often use the uniform distribution over -1 and 1 for all the entries in A, or a standard normal distribution with mean 0 and variance 1. But it turns out the things that we're going to talk about basically hold no matter what distribution you use right here. And this particular feature map, when you combine it with the perceptron hypothesis class, has its own special name. And it's often called the random kitchen sink. If you look in a lot of machine learning libraries, they'll have a model like their whole documentation page just for a random kitchen sink. And what that is just this particular feature map applied to the perceptron hypothesis class. The vast majority of models in use are somehow just particular feature maps applied to the perceptron hypothesis class. The random kitchen sink is so it seems weird, like somehow just selecting features at random, why on earth would that be good? But it turns out that it's actually state of the art for many, many applications. And this is true up to the present day. It was first introduced in 2006, and in 2017, this idea of the random feature map received what's called the Test of Time Award at this conference. Used to be called NIPS, now it's called NeurIPS, which is sort of the main, one of the biggest machine learning data mining conferences there is. And in a little bit, we'll take a look at the video of the author explaining why he likes this. But first, we'll talk about the VC sort of properties of this. Maybe before part one here, any questions about the definition of this problem, of this A matrix? Okay, so here, how does E in vary with D prime? It's very similar to the PCA that if D prime decreases, so if we reduce the number of dimensions, then the size of our hypothesis class is going to somehow decrease. That'll imply that the size of H phi is going to decrease. And when we have fewer hypotheses to pick from, that's going to imply that our training error, so the E in is our training error, is going to increase because we just have fewer hypotheses to pick from. And similarly, as D prime increases, that'll imply all the opposite things. Any questions about why those chains of statements follow from each other? Okay, so then a natural question to ask is that if the random feature map and the PCA both have the same exact form, it's just that this A matrix is different, how do they compare on their training error? They both follow the same pattern, but yeah, which one is going to be better in what situations? In general, you can't predict necessarily which one's going to be better. There are, but the EN for the PCA, for the random features has this really nice property. And that's that as long as if D prime is theta of log of D, that'll imply that En of GH is approximately equal to our training error of GHB. So this one on the left-hand side, this is the G with the subscript H. And G with a subscript H. And so that's the hypothesis without doing any feature map. Hypothesis with no feature map. And this is the hypothesis after the random projection. Here, exactly what it means for these two things to be approximately equal to each other is reasonably difficult to formalize. It'd be like a graduate class in geometry, discrete geometry, which would be needed to formalize this. But this is a really powerful statement that we can like dramatically reduce the amount of dimensions that we're using. So like if D was originally in the billions, we can go down to the hundreds, dramatically reduce our dimensions without a meaningful loss in our training accuracy right here. PCA has no similar guarantees. And in fact, reducing the dimension by just one on PCA can arbitrarily change your training error. But for some reason in like technical interviews, people like to ask about PCA. They don't like to ask about these random feature maps, but the random feature maps are really like much more powerful in practice. I've actually never personally been in a situation where PCA has been useful for me, but I use this random feature map like all the time. So we have, I don't know, this is sort of like an, I don't know, intuition-ish statement that you can reduce your dimensions by a lot and still keep a similar training accuracy. But in practice, like really the best thing you can do is do them both and use whichever one has the lowest training error. Lowest training error. We're going to see here in a second that they'll both have the same generalization error. And so whichever one has the lowest training error is going to be the one that's going to perform best on your problem. Any questions on that so far? Yeah, no.
I want to understand.
You're saying, how does this stuff in orange right here relate to the question statement? Yeah, so the stuff in orange right here is not actually, I guess, a direct answer to this question statement. Really, only this first stuff and this first like clause in red right here is a direct answer to this. But the reason we're asking this question is because we would like to somehow use whichever model has the lowest training error. And so really the only way that you can know which one has the lowest training error is you train it and see which one has the lowest training error.
So basically, like, they don't compare to themselves.
Yeah. There's no formula for comparing them. Yeah. So part 3, what is the VC dimension if D prime is less than or equal to D? I think I mentioned this in passing before, but for any linear feature map, so phi of x equaling something like x transpose A, then the VC dimension of H sub phi will be equal to the rank of the A matrix over here. The rank of the A matrix, the rank of this matrix is guaranteed to be less than or equal to the max of D and D prime. Sorry, not the max. It's also true for the max, but it's a better statement to say that for the minimum of the dimensions of the matrix. The rank of the matrix is at most the smallest of the dimensions of the matrix. And so if in the question up here, it's saying D prime is less than or equal to D, D prime is less than or equal to D, so D prime is the minimum. And so the rank is D prime, and so the VC dimension is D prime. And so the main sort of advantage of using this random feature map is that it gives us a really easy way to reduce our VC dimension if we need to for some reason. So again, if I use the example of going from billions of dimensions down to like hundreds of dimensions, if we have billions of dimensions, our VC dimension is billions, so we need billions of data points. But if our VC dimension is only hundreds, then we only need hundreds of data points. So this can really easily and drastically reduce our VC dimension for us. What is the VC dimension if D prime is greater than D? If D prime is greater than D, then D now is the minimum of those two dimensions. And so the VC dimension will just be equal to D by this same formula up here. This would imply that at least from a like generalization statistical perspective, that it never makes sense to have D prime greater than D because you can't like increase your VC dimension. You can't increase the VC dimension with this random feature map. Which implies you can't make your training error get smaller. It's a little bit like at a surface value contradictory to what I wrote up above, where I said that increasing D prime is going to decrease your training error. I'll come scroll back down here in a second. But up here, I said that increasing D prime will decrease your training error, but that's only true in the case where D prime remains less than D. Once you get out of that regime where D prime is greater than D, it's no longer true that the training error will just be constant. And so again, the reason why for all of these different feature maps, all of these different models, the reason we're talking about all these things, we want to know like what are the conditions when we might use them, when it might be beneficial to use them. And so the answer is that we need to reduce our dimensions. So our EN is already low, already small. But for example, our generalization error is large. The goal of using this, of decreasing our VC dimension, is that we won't change our EN too much. And again, we can go down to, under very general conditions, down to a logarithmic size in our dimensions, keeping a very similar EN. But our generalization error will go down a lot with this feature map. So it's very counterintuitive that just using like random projection, random features can work, but one of the most powerful techniques that people use in data mining today. Any questions about any of that? Okay, we'll switch to a video real quick to wake us all up. Go to the room PC. So this won't get into the Zoom recording, but the actual video itself is just this video right here. And we'll just listen to the inventor of the random kitchen sink talk about it for a couple of seconds. The whole presentation is really accessible, so it's worth watching. At this point, though, one of the main things he talks about is runtime considerations, and we haven't talked about runtime stuff yet. So at this point, it wouldn't make sense, but like a week from now, then the whole video would make sense. So let's play it. Hopefully there's sound.
Still use random features at work. I like to get creative with random functions and adapt them to the problem at hand. When they work well and I'm feeling good, I say to myself, wow, random features is so powerful in practice data set. Or if I'm in a more somber mood, I might say, huh, this problem wasn't hard at all. Even random features cracked it. It's the same way I think about ERC.
Okay, that's all for our insight from him, just that, wow, it's amazing, or it's just an easy problem. But most problems that people care about turn out to be really easy problems like that. So a good tool to use. Okay, this next problem 4 right here, we're not going to go over this. I'm not going to write the answers, but this one is using a feature map on the perceptron to define what's called the decision stump hypothesis class. And decision stumps, again, used very widely in practice, and we can understand everything that we need to understand about them by just using our VC techniques and combining this feature map with the perceptron hypothesis class. The textbook has all the information that you need for this problem. And yeah, so 3.15 in the textbook has what you need to fill in for these. Okay, so a little bit more, keeping going onto these single feature transformations. All the transformations we've seen so far are somehow applying to like every feature at once. But a lot of the feature transformations that people do in practice are just like individual columns at a time. And this is a very common one, problem 5 right here, definitely one that you'd need to know for like a technical interview or a midterm in this class. So the idea is that many features are discrete. So a particular column in like your data set might have just these integer values, where each of these integer values are somehow representing like information over here. And this is actually a real life example taken from a bank data set from a previous capstone course. And the bank, for determining its loans, whether to loan to somebody or not, had a feature that was somehow discrete or categorical like this, where each of these numbers corresponded to these sorts of values. And there's like no relationship between any of these values at all. Like being 6 is not like a lot better than 1, or there's no, yeah, they're all just like somehow totally distinct things. And the idea here of our feature map is we'll do a one-hot encoding. So that's the name of this feature map, a one-hot encoding that converts these discrete columns into like multiple Boolean columns. So here, instead of having like if our original data set of like X at position I was equal to 3, then our new transformed data set will be 0s at position 1 and 2, a 1 at position 3, and then 0s at all the other positions. So it's called one hot encoding because you put a 1 in the location where the original feature value was located at. The reason for doing this is because, especially with a perceptron classifier, this is going to greatly improve your E sub n. Because now you can sort of actually take advantage of each of these different categories. With the perceptron, you always just pick a line and somehow divide the data set based on that line. And there's no like meaningful line to draw between any of these things, because again, they're all very discrete. But now you'll have meaningful lines that you can draw between these 6 values. And so the one hot encoding very often greatly improves your training error. That's one of the main things to know about the one hot encoding is it greatly improves your training error. And again, every time I see E sub n in my head, I actually pronounce that as training error. Okay, so another question we need to ask ourselves is, how does this affect our VC dimension? And so if we have C possible values, so 6 values in this case, but C values in general, then our feature space will have this D prime equals D plus C minus 1. We're deleting this original column from the data set and adding, in this case, 6 new columns. So D plus C, then minus 1 for deleting the original column. And again, in general, I always just think about that in like big O theta notation, D plus C. And that's what our new VC dimension is going to be equal to. So dVC equals D prime, which equals the theta of D plus C. So that will reduce our will make our generalization error a little bit worse. But in most cases, like the C value here is not super large. And so it's not going to make our generalization error too much worse. Like in this case, only 6 values here. We don't need too many more data points to make that work for us. In some cases, though, the number of discrete values can sometimes be extremely large. For example, C might be the city that a person was born in, and there are millions of cities in the world. I looked it up, and there's about 4.1 million cities registered with the United Nations geographical body that tracks cities. And so if you do that transformation, then your VC dimension is going to increase by millions. So if our DVC increases a lot, so increases a lot by millions. Our fundamental theorem of statistical learning, the only theorem that you have to have memorized, says that our generalization error, the E in minus E out, is going to be equal to O of square root of DVC log n over n. So, and you can basically ignore this log n term, that it's basically proportional to the number of VC dimension divided by the number of data points. And so we need to really increase the number of data points to get the same generalization error. Are there any questions about why any of those things follow from each other? Your goal, yes.
If TBC is the number of cities, what would
So if we're imagining that our data set is, should we give a loan to somebody or not give a loan to somebody, maybe we have just 2 features: their city that the person lives in, and which is encoded categorically, like up here, and their net worth. And so the VC dimension of that original problem would just be 2. But then after this feature transformation, the VC dimension would jump from 2 to 4.1 million. I don't know, did that answer your question? Or
increase the data points?
oh, then so yeah, then how would you increase the data points? Well, your bank would have to we wouldn't be able to make any. Yeah, it's a good question. One of 2 things would happen. Either we would do our learning with this new data set in the original amount of data points, in which case our generalization error would be very, very large, and we would probably not get good results. The model that we generate would probably not generalize to future results. Maybe we only have like 1 person from Claremont, and so whether that person happens to have a high net worth or not a high net worth would totally skew the model's understanding of people from Claremont. And then, yeah, how you actually increase the size of the data set, that's not something that you can do automatically. That's something that would have to be done at like a business level decision of people go out and study the problem more, somehow generate new data points. Maybe you can go back into your historical archives and somehow extract more data points from that. Or maybe you just have to start giving out loans to random people to figure out, to gather that data somehow. So yeah, the adjustment of the VC dimension is something that we can do programmatically, something that there is a business person doesn't have to be involved in this adjustment right here, but adjusting the number of data points somehow involves like a business decision of actually physically doing something in the real world. Did that answer your questions? Good question. Any other questions on this problem? Okay, your goal as you're preparing for Wednesday, again, this kind of question is not the sort of thing that's going to be on that quiz. But as you're like studying the equations or studying the definitions, should be to like be studying them in a way that's going to make these sorts of analyses like obvious and trivial for you, so that you don't have to think about something like this. Like when I am sitting talking to other data mining people, this entire discussion that we just had would pass through in like 5 seconds, and there would be no like, we would just all know that we're on the same page because we all know these definitions. And so you want to get to the point where this is something that you don't really have to think about. This part B, how do you fix this problem? This is something that is now something that you're a little bit more thinking about. Like, how do we fix this problem? So again, the problem is that our generalization error is too high because our VC dimension is too high for our number of data points. So somehow we have to decrease the VC dimension. Somehow we have to decrease the VC dimension. Decrease the VC dimension. We must decrease the VC dimension. And we've seen 2 ways of doing that so far. The PCA transform and the random feature transform. Either of those would be reasonable things to suggest and try. PCA or random features, reasonable things to try. Because both of those things, they're dimensionality reduction techniques. They give us a tool for decreasing the VC dimension. Any questions about that? Okay, a couple of other operations for us to talk about. So these ones are a little bit simpler, but described maybe more mathematically, so maybe more abstract. So here, this phi right here is we're just, it's called the mean centering transformation, to calculate the mean of all your data points and subtract that off. This doesn't affect the VC dimension at all. It doesn't change our, it doesn't change what we can shatter or not shatter. So no effect on the VC dimension, which implies that the VC dimension of HV remains equal to D. And this might, well, so the generalization error is not going to change. The training error, E sub n, may or may not decrease. And so again, you can just try it. Does the training error go down? If it does, then that was a good thing to do. And you're going to generalize just as well as you generalized before. So try it. If En goes down, then keep it. It was a good thing to do. It's a very common theme about the training error is that, at least from an introductory level, there's not a whole lot that we can say about proving something is going to decrease or not decrease the training error, but you can always just try it. The training error is something that we can easily measure. And so you can always just try it. If it makes the training error better, then keep it. If it doesn't make the training error better, then throw it away, do something else. Any questions about that? Okay, the very last problem down here is very similar. This is I'm calling it the range normalization feature transformation, where we rescale all of our features to so that they're between -1 and 1. And as a formula, that would look something like this. Here, just a subtlety of the book's notation is that this fee right here, this is the lowercase fee. That is the lowercase fee. That is upper, lower, and upper. And whenever the book uses the lowercase things with a subscript, that's referring to a particular index in this thing over here. So you pass the x vector into the phi function. It's still a vector valued function, but we're only getting the I index out. So they use the lowercase phi, and xi, the ith index of the x vector right here, divided by alpha I, where alpha I is the biggest absolute value of the xi components. And so this will scale everything down to be between -1 and 1 on all the components. Again, how does this affect the VC dimension of our hypothesis class? Well, it doesn't. We can still shatter anything of any data set of size D. So the DVC still equals beta D, just like before. And again, when should you use range normalization? Well, you just try it. If the EN goes down, then you can keep it. Doesn't affect our generalization error, this sort of like mystical thing that we can't actually measure. And so all we have to do is look at the training error, which is the thing that we can measure. And so if it makes that better and keeps the generalization error the same, then we should do it. Any questions about that problem? No? Yeah, so that's a good question. The question is, why would you do this? In some sense, so it's anytime you ask these why questions, you're getting a little bit philosophical. In some sense, the only answer to any of these problems about why would you do it is the training error either goes down or it goes up. And if the training error goes down, that is a sufficient reason for why you would want to do it. Yeah, that you try it, see if the training error goes down. I think so. Part of your question is also somehow, what are the conditions under which the training error is likely to go down? That's getting a little bit more importantly into the why. And that's for all of these feature map functions. That's an extremely difficult question to answer. It's an easy question to state informally, but you end up needing graduate level math and geometry to talk about what are the conditions which would cause this to go down. So yeah, in practice, even the people who have that graduate level math, we might sit and think about it, but it's so quick to just try it and run it that we'll just try it and run it and do that if it's better.
Basically, all the stuff you would top of this stuff you want to try.
Exactly. So yeah, we're basically just building up this toolkit. Here's the list of things that you can try to see if it decreases the training error, and if it does, then keep it. In this case, these last two problems keep the generalization error constant. So it's easy to try and just try it, and you know that it can't make the generalization error worse. Things like the like this sort of transformation, they will make the generalization error worse. And so if you don't, so you have to understand, do I have enough data points to even consider trying this type of transformation? And if you have a small value of what I called C, this number of items, then you will probably still have enough data points. If you have a large value of the number of items, then you'll have to do something else to counterbalance things. But yeah, so I guess it's a very empirical like field that's somehow guided by intuitions from these theorems, but not like apply this theorem and it will tell you what to do. Yeah. Kind of.
Would it be like reasonable intuition, say, for example, related to the loan problem that we're discussing? If one of the features is like income, so that's like on a different scale, and say like if you want to scale them all down, so when you went to model, would be overweight income's importance over age.
Yeah, so the question is like, if we have things of somehow different magnitudes, does that make give me intuition that range normalization might be a good thing to try? And possibly, that's certainly the situation where it might help, but I could come up with artificial situations where you, when you have that large discrepancy, it's not going to help, but it'll make things worse. So yeah, so like the reason these proofs are hard, like to actually come up with formal statements, is that you have to come up with you have to formalize things about the probability distribution that the data is generated from, and talking about the shapes of probability distributions is really hard to do, or requires a lot of technical things to do. So yeah, I don't know if that answered the question or not, but that's the answer. Karen?
Do like prepackaged scalar models already do dimensionality reduction?
Question is like, so all of these things that we've talked about are implemented in sklearn. None of them happen automatically. You have to go through there and find the flag that does it and enable it individually. That answer your question?
Yeah, is it something that you should always implement, or is it like based if you need to reduce?
When I'm doing a learning problem, I would never start off doing any of these transformations. I always start off with logistic regression, which is closely related to perceptron. And then look at my training error and generalization error. If my training error is really low, then I won't even consider any of these things. If it's really high, then I'll try to think about why is it high. If I have these categorical features, then this is a very good thing to do to reduce training error. But yeah, it starts getting into very like alchemish sort of things at that point. All great questions. Happy to keep talking about this with anybody who would like to, but that's our end of class for today. Wednesday again, we will have the quiz and we'll start talking about computation stuff.
Thank you.